solid state physics laboratory, we perform different experiments. So, we have some experiments for studying the property of magnetic properties of solids. So, today I will discuss about about an experiment how to measure the magnetic susceptibility of paramagnetic or diamagnetic material using a method is called Queen's method. So, measurement of susceptibility of diamagnetic or paramagnetic material by Queen's method. So, theory of this method one should understand properly. Queen's method is used to determine magnetic susceptibility of diamagnetic or paramagnetic materials in form of a liquid or an aqueous solution. Okay. So, you have to prepare solution of the material, magnetic material which you want to study. Now, using that solution we perform experiment. Now, when we are going to basically susceptibility if you want to get, you have to measure magnetization as a function of magnetic field. Then susceptibility is defined by m by h. So, magnetization per unit magnetic field. So, that is the susceptibility. So, when we are going to measure magnetization in laboratory, so there are two methods. I should say that there are two ways. So, magnetization I will change the magnetization applying the magnetic field. Now, for each field, what is the magnetization? So, that I have to measure. That means I need device which will sense the magnetization, which will sense the change of the magnetization. So, to sense the magnetization, there are two ways. One is induction method. So, if you take a coil, induction coil, and keep close to the magnetic material, means close to the magnetization, so there will be flux link with the coil, and if there is change of this flux coming from the magnetization and link with the coil, if that flux changes, then there will be proportional induced EMF in the coil. So, measuring this induced EMF in the coil, we can basically, we tell that we are able to sense the magnetization. So, this is one way, induction method. Another method is called this force method. Okay. Force method, if magnetic metal having the magnetization is in a inhomogeneous magnetic field, means magnetic field will change as a function of distance. If you keep the material in this inhomogeneous field, then there will be force acting on this material due to the magnetization, and so that force have to be balanced with some other force or other force, opposite force. So, if you can balance these two, then from this balancing equation one can sense the magnetization, one can measure the magnetization measuring this basically the parameter from this balance equation of these two kind of force. One is magnetic force or force due to the magnetization, and another compensating force in opposite direction. So, this is called force method. So, Quinn's method is basically force method. So, magnetic moment can be measured either by force method or induction method. Okay. So, force method is basically the measurement of the force exerted on the sample in inhomogeneous magnetic field. So magnetic metal have atoms. So, each atom is have the magnetic dipole moment, or if it is paramagnetic diamagnetic material, then there will be there is no magnetic moment, net magnetic moment of the atom, but in presence of magnetic field there will be induced moment in the atom. Okay. So, this induced moment basically in presence of magnetic field. So, that is the origin of basically diamagnetic material, origin of the diamagnetism. So, that means either it is induced moment, magnetic moment, or the natural this spin magnetic moment, okay, or orbital spin orbital magnetic moment. So, atom will have the moment. So, now these moments are so these moments, each dipole moments or the total moment of the whole material. Okay. So, that moment when it is in a magnetic field, so it will feel torque, it will feel force, it will feel torque, it will have the potential energy. So, potential energy U defined by U equal to minus m dot b, minus m dot b. M is the magnetic moment, okay, magnetic moment, dot b, b is the magnetic field induction, magnetic field in the material basically, this b. So, U I can write this now here dot product, this m dot b. So, m b cos theta. Now, as I told this, in material you have dipole, either induced dipole or the atomic dipole due to spin and orbit. Now, this dipole moment are randomly oriented in the material, So, here m dot b basically average cos theta, you will take, we have to take average cos theta. So, if you take average cos theta, so that is why this I have written here, this half this term I have written. So, this is basically minus m b is, if it is in b, this mu 0 h, okay, mu 0 h, mu 0 is the permeability in air, and this half this term has come due to this average cos theta. Okay. So, now potential energy, if this force, it is defined as minus grad u. Okay. So, grad is basically this d by dx I can write for one dimension, d by dx I can write. Okay. So, d by dx, and then this u term is this. So, where m and h are there. So, mu 0 is constant, half is constant, minus sign and this minus sign will go. So, half m mu 0 d h m by dx. So, now m magnetic moment Magnetic moment is basically, you can write total moment of this material. Here this M, we have considered total moment of the material. Okay. So, if magnetization is defined by this total moment of this material divided by total volume of the material. So, this M, small m is capital M into V, capital M into V. So, and this I can write chi M is chi H. So, if I put M is chi H, so this chi H is basically here M is mv I have written, this total moment mv I have written total moment. So, now this chi is in place of m I can write chi H. Oh, okay. So, I am searching where is V. So, for V equal to 1, okay, for unit volume. If we consider unit volume, so this I can write Hm. So, m is chi H. So, chi H square. So, chi is constant. So, dH square by dx. Okay. So, this force depends on the magnetic field as a function of x. That means, magnetic field if it is constant over a distance, so there will not be any force. So, if magnetic field varies over a distance, so then this will give force. Okay. So, differentiation of H square as with respect to x, if it is not 0, then only it is possible if you have inhomogeneous magnetic field. So, in constant field there is no force, but in inhomogeneous magnetic field there will be force. So, that is why I told. So, this the force present only when there is a inhomogeneous field. Magnetic material is in the inhomogeneous field, and this is for a per unit volume, because V equal to 1. So, that is energy density. So, what will be this if this is force? Okay. If this is force, now here I have written force. If you force into dx distance, okay. So, there is work done or energy density, you can tell that will be half mu 0 chi H square. Okay. So, this will be work done or energy density half mu 0 chi H square. Okay. So, now if I take a liquid, or solution of the magnetic material, either paramagnetic or the diamagnetic material. So, in tube if I put this solution and this tube is placed between pole pieces of an electromagnet for magnetic field. So, we have to place in such a way that upper surface of the liquid is at the center of the poles, okay, at the center of the pole pieces where maximum field H, and the lower bottom is outside of the poles where minimum field H 0, this is H, this is H 0, then energy density. Okay. So, say WH energy density due to the magnetic force. So, that is half mu 0 chi H square I told there. So, H square minus H 0 square. Okay. So, you have seen this integration. So, integration over the x, integration of f dx equal to integration of dA square. So, there we have written result just 0 to h, then it will be h square. Now, here if not 0, say h 0 field is their minimum field. So, then this will be h square minus h 0 square. Okay. Now, what will happen? So, this is happening because of the, so this energy density whatever we are getting, that is because of force, and the dx, integration over dx over the length whatever we are writing. So, it will feel force, this liquid will feel force, and basically it will change its height, Now, because this liquid is feeling force due to the magnetic field, and from where this force is coming because of the presence of the inhomogeneous magnetic field. So, this liquid will move up or it will go down. Okay. Now, if say it is easy to understand if you consider that it is a move up, that means from its before applying magnetic field whatever the surface position, okay. So, that was the balance position, not balance, the equilibrium position. Now, this surface is going up due to the magnetic field. Now, if you can measure this change of height, then how much liquid has gone. So, now this there will be gravitational potential energy, right? There will be gravitational potential energy. So, this WH, it is magnetic energy density, and this will be balanced with this gravitational potential energy density. So, gravitational potential energy density, if I write that height is h, okay, that height increased, that is h. So, rho g h, mgh. So, m in this case density we are considering. Okay. So, that is why we can write rho mass per unit volume. So, then this gravitational energy density W g, and this is for magnetic field it is W h. So, these two will be equal, because this due to the magnetic field it is going up. Now, due to the gravitational downwards force it will try to come down, but this is the balanced position. So, there these two force, gravitational downward force and this magnetic upward force, these two force has to be equal in equilibrium condition, then it will reach to the equilibrium condition, and for that whatever height we have to measure. So, that is h. So, in equilibrium this equal to this. So, if we equate these two, so we will get chi equal to 2 rho g h by mu 0 h square, when h 0 is approximately 0. Okay. So, this formula we will use as a working formula for this experiment. So, one has to remember that in which condition we are getting this formula. So, that is important. Now, this formula here we have considered that this the sample liquid, that surface in a tube, that we will put at the field H, and other end of the sample it has to be outside of this magnet, then only you will fulfill this condition, this H 0 equal to approximately 0. Okay. And here H, what is H? In presence of magnetic field, what is the height change of the liquid? Okay. So, we have to do the experiment, we have to collect the data. So, experimental data we have to record. What we have to do? So, we need magnetic field, so we will use electromagnet. So, whenever you are going to use electromagnet and you have to place your sample, in this case we have to place the tube contain liquid. Okay. So, we have to keep these pole pieces, that gap at a particular gap. Okay. So, we have to calibrate the electromagnet. So, calibration of the electromagnet using the Gauss meter and Hall-Pruff, that first one has to do. So, that is calibration of the electromagnet. Second, that in that formula you have seen rho is there. So, though that rho, what is that? Density of the solution. Okay. So, we have to prepare solution and we have to measure the density of that solution liquid. Okay. So, that is using this formula one can find out if it is water solution. Okay. So, then here W2 minus W1 divided by W3 minus W1. So, mass of the empty bottle, we will take a bottle. So, we will weight that, take the weight of this bottle W1. Now, bottle plus liquid W2. Now, bottle plus water, that is W3. Okay. So, W3 minus W1, that means water, W3 minus W1, that means the water, volume of the basically this that will be the mass, of the water. Okay. And if I take W2 minus W1, so then it will be the mass of the liquid. Liquid means a solution. So, water, and there I have put the material, okay. So, this material resolve in this water. So, that weight is W2. So, here basically I will get this weight of the, this is a weight of the liquid divided by weight of the water into the rho water. Okay. Means density of water. So, from using this formula we will get the density of liquid. Okay. So, one has to find out basically density of the liquid which we will use for our experiment. So, that you have to measure. Then measures height using travelling microscope at different magnetic field. Okay. So, this is the basically main part of the experiment, that we will apply magnetic field for different magnetic field. What is the height change of the liquid? So, using the travelling microscope we will measure the height of the liquid. Now, we have data h versus a small h, that is the height, versus the magnetic field. So, now h versus h square, magnetic field square, we will plot that graph. Now, from that graph we will get the slope, and from that slope one can find out the chi, right. So, this in slope chi and other constant parameter will be there. So, that constant parameter are known. So, we will be able to find out the chi. So, this is the procedure or theoretical part of this experiment, Quine's method, how to find out the chi as a function of magnetic field. So, that experiment we will demonstrate in our laboratory in next class. Thank you.